Interesting, isn't it? Well, that's what we're going to learn today. But before that, I have a question for you. Say these black dots are restaurants, and this is you. Now, you want to find out restaurants that are nearby. So, the restaurants that lie within this search area. So, my question is, what do you do? Do you go on searching for do you go on searching for the distances of all the restaurants out there in the world? Do you go on searching for if all these restaurants lie within your search area? There are millions of restaurants out there. And if you go on searching for all of them, you go on finding their distances, that will ruin your performance. So what do you do? Well, we'll answer that in the later part of this video, but let's start with the video. Okay. So hello everyone. In this video, this is the first video in our new series of spatial indexing. So what's spatial indexing? So the data. So there are two types of data basically. The data that is arranged in a linear format. For example, the one-dimensional data, like you have data in the form of an array, and there is data that is about physical space. So data that is represented in the form of coordinates. So if I have to search this data, this spatial data, that is what we do by the help of spatial indexing. And Quadtree is one of the tools to search a spatial data. So let's look at the contents of today's video. So we'll begin with what a quadtree is. Then we'll see a point insertion algorithm, how to insert a point into a quadtree. Then we'll look at range query algorithm. That is, how do you find the nearby restaurants? That's what we did. And then use cases. Where do you use a quadtree? And where you should not use the quadtree. Okay. So let's begin. Let's begin with the definition. So now there are two representations here. The left one that you see is the spatial representation. So a quadtree has four quadtrees inside it. It has four parts. They are northwest, northeast, southeast, and southwest, indexed by 0, 1, 2, and 3 respectively. Now, each of these parts is actually a quadtree. You see this quadtree, northwest, northeast, southeast, southwest. They are represented by the black boxes because they're internal quadtree. And this is the tree representation. So this is the outer quadtree, and this is the inner quadtrees: northwest, northeast, southeast, and southwest. So this is the representation that we are going to follow ahead. I mean these indexes. Okay, this representation. Okay, all right. Now there are two more important attributes of a quadtree. The another is one is capacity. Capacity. Now capacity is an important thing. What it tells is, see, a quadtree splits when it exceeds its capacity. Okay, so before that, let me tell you that the quadtrees that we are discussing here are point quadtrees. What that means is that the splitting happens when the feature under consideration is a point. Okay, so we are all the features that we are going to look here will be points. So the capacity tells us when should you subdivide a quadtree. Okay, is divided. Now this is something that you use for implementation purpose. So it tells us if the quadtree under consideration has been divided. Okay, all right. Then let's move on to the next part, inserting a point in a quadtree. Now, how do you insert a point? So this yellow box is your outer quadtree, and its capacity is 2. And we have inserted the first point P1 here, so it lies inside this point. You insert another point P2, it lies inside this point, but now it has reached its capacity. It has reached its capacity of 2. So now what happens if you insert any more point? It splits. So you see the outer quadtree, yellow one, has split into its inner quadtrees, inner blue quadtrees. And the points that were inside the quadtree earlier have been transferred to its child quadtrees now. So P2 goes to 0, P3 goes to 1, then P1 goes to 2, and 3 has nothing. So that's why it's grayed out. Similarly, you insert more points. P4 is inserted. Now, again, this quadtree has reached its limit. So now if I insert one more point in this quadtree, it splits the points that were here in this quadtree, that is 1, have been transferred down into its child quadtrees. So now this quadtree, it gets P3, P4, and this quadtree, it has P5. Now, talking about indexing. So you know that these quadtrees are indexed 0, 1, 2, 3 as we move northwest, as we move clockwise from north to west. And now whenever a quadtree is subdivided, the each of its child quadtrees gets an index which is decided by like this. So the quadtree, so each of the individual quadtrees, uh, its index is determined by its individual index, which is suffixed to its parent's index. So this quadtree has an index of 1, and this child quadtree has an index of 0. This has 1, and this has 2, this has 3. That's why it got 1, 0, 1, 1, 1, 2, and 1, 3. If this child quadtree is divided further, then it will be further divided into 1, 2, 0, 1, 2, 1, 1, 2, 2, and 1, 2, 3, like this. So that's all about indexing and about inserting a point in a quad. Now, the next part is answering the question that we asked in the beginning of this video. How do you search for nearby restaurants? Now, this is your quadtree, the outer quadtree, and this has been divided into sub quadtrees. And these black dots are all the restaurants, and this red dot is your location. And this is your search area. You want to find out the restaurants that lie within the search area. Okay. So the range query algorithm, what does it say? It says that you start with the outermost quadtree. You check if it intersects or overlaps with the search area. Now, outer quadtree is this yellow one. Does it intersect with your search area? Yes. So what do? Next, you ask yourself another question. Is the quadtree subdivided? Yes. It has been subdivided into these 4 quadrants, 4 blue quadrants. So you check for all of the child quadrants. So you start with this child quadrant. Now again, does this child quadrant intersect with this search area? Yes, it intersects. You see, this is the intersection. So you again go on checking for all of its child quadrants. So you see what we're doing is a DFS traversal. So you check this quadtree again. Does it intersect with this search area? No. So you skip it. You go to this. You check for northwest. Now you check for northeast. Does it intersect? No. So you skip. Now you go to southeast. Now does this intersect? Yes, it intersects. So what do? It intersects and it is subdivided. So you check for all of the inner quadtrees. So you start with this quadtree. Does it intersect? No. Skip. Does this intersect? No. Skip. Does this intersect? Yes. Now again, you ask yourself again the question: is this quadtree subdivided? Is this quadtree subdivided? No. So if it is not subdivided, it means all of the points that are there are inside this quadtree. So you have to check for all the points that are inside this quadtree to check if they are contained inside the search area. So you check for this point and you check for this point. Are they contained inside the search area? No. So this is how you go on searching for all of the quadtrees out there. And finally, this is the result you get. So the black dots are the restaurants that you searched, and the gray ones are the restaurants you did not. So that saved us a lot of time. Okay. So how many are these? 1, 2, 3, 4, 5, 6, 7. So you searched for only 7 restaurants, and maybe you skipped around 10 to 15 restaurants. So, well, this is a trivial case, but in actual life, you will skip millions of restaurants out there. There are millions of restaurants in the world. And if you want to find out restaurants within a 5 to 10 kilometer range from you, you will skip millions of restaurants. So that is where that is where its use comes into the picture. Okay. So let's look at some more of its use cases. Okay, so one of the most important use case is in game development. So it is used for collision detection. So say this game has many players, and you have to find out if there's a player and you have to find out if it collides with any of the other players. So you do not go on checking for all of the players out there. you check for only the screen. Okay, this your screen is a search area now, and you check if the screen overlaps any of the quadrants out there, and you check for players only inside those quadrants. Similarly, in JSON mapping, uh, whenever you open a Maps app, what do you see? You see the world map. Okay, you see the world initially. You don't see it unless you start the GPS. You don't see it narrowed down to your city, or you don't see the streets initially. But as you zoom in, you see the streets. So what happens is, as you zoom in, your search area it is refined. Now the screen is your search area. So you only see the quadtrees. It only searches for the quadtrees that intersects with your search area, with your screen. And all of the other parts, all of the other zones, they are discarded. They are not searched. So it saves a lot of time. Similarly, if and why is it better than grid search? Now suppose there was data that is sparsely distributed, and it is just collected at one point, or it is just concentrated at some location. So the grid search will fail here. It will go on searching for all of the grids out there, all the cells. But what will a quadtree do? It will just not search all of them, because it will divide them into quadtrees, and will search for only those quadtrees that intersect with your search area. Okay. All right. Now, when not to use a quadtree? Okay. To answer this question, uh, this is the first point, tree degeneracy. Now let's look at this case. Okay, you have seen how we add a quadruped, how this split happens. You add a point, and this is how it is split. Now, but if I keep on adding points at just one location, I keep on piling those points. What happens? Okay, oh, sorry, 1 point here, here. You see what happened? It's suddenly it's suddenly all of the trees have been defined. Okay, so this quadtree, then this, then this, then this. So what happens is an infinite loop of infinite loop takes an infinite loop of quadtrees runs, and uh, it ruins your performance. So what you get is a skewed tree. What happens is it does not improve your performance. It is This is just big of and search. Okay, so that is a problem, tree degeneracy. The second is dynamic data. Now, uh, Quadtree works best for static data. The reason I took the restaurants example here was that restaurants are static, they do not move. But suppose instead there were drivers out there. Now the drivers keep moving. So what happens is, if a driver moves from one quadtree to another, his location changes. So what you have to do is, you have to remove that point or that location from that quadtree, update that quadtree, and insert that point into another quadtree. And that takes time. And the gain that you have obtained by using a quadtree instead of a grid, say it was 10 seconds. So the time it takes for these added operations, that is removal, updation, and deletion, sorry, insertion, these take say 15 seconds then. So what happens is, your performance is actually degraded. So there is no use of using a quadtree actually. So what do you do in that case? Well, we'll look at that in the next video. So stay tuned, and thanks for watching.